In this video, I'll be teaching you the basics of network programming with Python so that you can make online multiplayer games like my games PixCarts or Gunslaw. I'll be using the sockets library and also the struct and threading libraries, all of which are built in with Python, so you don't have to install anything. So in that sense, it's agnostic to whatever rendering system you're using. In this case, I'll be using Pygame though, just so that I have a game to make multiplayer. The game that I have is Tic-Tac-Toe. So, I mean, everyone knows how Tic-Tac-Toe works, hopefully. And you just get 3 in a row, and whoever does that wins. And you've got like 9 spaces here. It's naturally a 2-player game, so it's an easy one to make a multiplayer game for this demonstration. As far as the code goes, we've got the simple stuff: drawing the letter, creating the window, drawing the board, placing pieces or letters, however you want to say it, checking for a win. It doesn't care what size board you have for this one if you change the size here, so you could actually easily hack this to be a bigger board. You can do like a 10 by 10 or something. And then here's the main loop, but we don't have to focus too hard on that because we're just communicating the board state and the player actions for the networking today. And once we've got all that hooked up, we'll see it all working. And in the end, I'll go grab my laptop, upload the server script to an actual server that I have on the internet, and I'll demonstrate how you can play a game like this over the internet. Anyways, the first decision to make is whether or not we use TCP or UDP. You can do some of your own research on this. There's a lot of arguments for and for different cases, but generally speaking, TCP is better for things that are less real-time, and UDP is better for things that are more real-time. And Tic-Tac-Toe is very much not a real-time game, it's a turn-based game. TCP has the idea of a connection, it does a lot of the stuff for you, so it handles checksums to make sure things are not corrupted, make sure everything arrives in order, and that everything actually arrives, whereas UDP has none of those guarantees. So in this case, we're going to be using TCP. A lot of the ideas built on top that we're going to be using are applicable for both protocols, but the idea of connections that we'll be working with is specific to TCP. So before we jump into actually writing the code, we need to think about how we're going to architect the networking portion. So the first thing to think about is that usually you're going to have a process that's receiving data while the game is running, and then you also want to be able to send data. And same thing with the server. The server is going to be running some regular calculations, and then you want to be receiving the data from different clients. So the way you do that at the same time without having to, for example, freeze the game while you go handle the networking stuff is to use threading. So threading is not multi-processing in that it uses multiple processors with Python. It's just asynchronous in that both of them can be running at the same time. Under the hood, it's just switching back and forth really quickly. But one of the things that comes with that is that Python has this global interpreter lock, which a lot of people complain about, but in this case, it's actually very useful for us. So it means that our different threads are actually sharing memory. And when, for example, the client receives data from the server saying that the board is in this state, it can just go ahead and update the data, and the renderer just has that data right there immediately without having to go through some like message queue or something to get it in. So it's very easy to work with in that sense. So for the threading, we'll be using the threading library. It's pretty straightforward. You just kind of point it at a function and tell it to run it asynchronously, and that's pretty much how that works. It'll make a little bit more sense once we get into that. So to start with our multiplayer functionality, we need to go ahead and create a server. So I'll just create server.py. We'll go ahead and import socket, and we'll also import threading. And on top of that, we'll also need time and struct. Like I said, threading is for the asynchronous part, and then struct is going to be, which I haven't mentioned yet, it's going to be so it can handle the binary data, because when you're dealing with networking, everything's going over in binary. So you have to be able to encode and decode that data. I'll get into that later. So let's go ahead and create our server. So I'll do this in the object-oriented way. We'll just create our class, and we'll create our host as the local address, and then we'll just create a random number for the port. We just don't want to clash with any other processes running on your computer. So if you don't know about just the general stuff with networking, there's the idea of your host address, or just the address of your machine, your IP address. It's what uniquely identifies a machine on the internet and then also local networks so that it can be accessed by other computers. It's like your address of your home, for example. It's how you know where it is. Now, the port is just an extra number that goes along with the address to indicate what you're trying to interact with, essentially. So different applications will be operating on different ports, and only one thing can use each port at a time normally. So you'll want to just have a somewhat random number. You can kind of look up the different ranges and what numbers you shouldn't use on the internet. When for example, the server receives data and it's on that port, it knows to kind of point it to this application that's interacting with that port, while other applications could be using different ports at the same time. So that's how that works. So we'll go ahead and save this information. And something I should mention about this address, in case you don't know, is the local address. This number always represents your local machine. So just because I put this number here doesn't mean that the other player connects with this address. I'll get into, when I actually use my server, what this might look like later when it's not the same thing. But in this case, while I'm developing, I'm on one machine, I'll be testing the server on this computer, and I'll also be testing the client on this computer, so all of it's going to be pointing at this machine. But when you host, your hosting address, usually you want it to be something like this. I don't want to get too into the weeds on interfaces, but sometimes it'll be like a different number if you want to like host on different interfaces that represent like different networks that your machine might be connected to, because you can be connected to multiple things at once. Anyways, some other things we'll need for this are a kill flag. We'll set it to false for now, because when you're dealing with multi-threaded stuff, it can kind of be a pain to shut things down. We also want a thread count, so we know when everything's been shut down. We'll add the information for the game itself running later. Let's create a run function, and then we can do a server.run down here, and that means that basically we can just run the script now and it'll call this function here in the server. For our main loop, we'll just throw in a try while true time.sleep 0.05, and then we'll do an accept keyboard interrupt, and then we'll put in pass for now. So what I'm doing here is just creating a loop that we can work with later. We'll want the server actively doing things periodically in a lot of games. So what I like to do is just have like the main thread that it starts on go into some sort of like a game loop, for example, and it maintains that. But then you'll do a keyboard interrupt at some point if you do Control-C in the console where it's running. You'll want to handle that properly to shut everything down. You might want to change this up depending on how you're closing your application, but in my case, I'll just be pressing Control-C in the terminal. Okay, now, so to receive a connection and let people connect to the server, we can go ahead and create another function to listen for connections. So connection, listen, loop. And then I want to do this as a thread, because if you think about it, you're going to have one part that's going to be listening for connections, and you don't want that interfering with the part that's running the main game logic. So since this is going to be its own thread, I'm going to do self.thread count plus equals 1, and then self.thread count minus equals 1, so that anything I write in between will be blocked off, so that if it's still running, we know that there's something running there. But once it's done, it just subtracts and it's done. Anyways, so we'll do with socket.socket socket.afinet, and then socket.sockstream as s. So what we're doing here is we're creating our socket, and socket's essentially the thing you interact with for all the networking purposes. It's the object that represents the interface to the outside world, essentially. And then what we're doing here is we're setting up a socket and configuring it for TCP. That's what the sockstream thing is for. And then it's like, I think sockdgram is for UDP. And then this part here is the address family. Now we want to set a couple things first. So we'll do set sock opt, and we'll do socket.sol socket and socket.so reuse address, and we'll set it to true. So this, you don't have to do this part technically. All this is doing is making it easier for the address to be reused. Something you'll find out is if you don't have this, if you kill your server, you might be waiting for a while before it'll let you start another one again, because it can take a little bit for your operating system to recognize that it's free for anything to use. And then the next part is to finally indicate that we want to set up our listener here, and we'll go ahead and indicate our host and our port. And then now we have to just receive this connection. So we'll do while not self.kill s.set timeout. We'll just set a timeout of 1 second so that when we listen, it doesn't hang forever. The reason we want to set timeouts is so that we don't get stuck in some sort of call for the sockets that can stop the thread from being closed down properly. We want it to be that if we set kill to true, it can exit this loop within a reasonable amount of time, which is why I put it at 1 second. So we'll do s.listen. Under this, we can do connection address equals s.accept. And then I'll do accept socket.timeout and continue. Time.sleep 0.01. The socket timeout error is what's thrown when our accept times out and there's just no one connecting. So we just want to move on and then go to the next loop. We'll be catching a lot of these in our different threads here, because you end up with 4 of them because you send and receive both on the server and the client. So let's go ahead and print out our new connection. It's con address. Let's go ahead and add our list of players. And we'll do if len self.players is less than 2, self.players.append, and we'll add the connections. So s.accept returns a tuple that contains the connection object and then the address. The address we can throw out in this context. You might want to use it for something if you just want to check what the address connecting is. When I'm actually on my server, I have it behind some other layers, so this actually doesn't really mean anything on my server. But this connection object is what we send and receive stuff through, and it's going to be pretty straightforward. So we just need to hold on to this object, and it represents this specific connection from that client. And then we do have to maintain the connections from multiple clients at once, which means we have to spin up more threads here, because you don't want to be waiting for another player to send something before it gets to like the second player to receive stuff. For that, we'll want to put in later spawn listener task. But for now, we can just see if our code to handle a connection even works. One last thing I have to do here is to actually start this thread. So we'll do threading dot thread, and then we set our target. So this, you just point it to a function and it'll run it asynchronously. You can also pass arguments as well, but in this case we have no arguments, so I don't have to do anything. So all this does is this right here will just start it for us, and it's kind of on its own at that point. And then on a keyboard interrupt, we'll just want to set to kill to true, and we'll want to def await kill self. Actually, we can move this and do await kill here and set kill to true here, and then we can say while self.thread count, meaning there's still threads running, we just sleep and wait for it to stop running, and then eventually you can just say kill. And once we get to this point, then we know all of the threads have shut down, because once we set the flag here, they should shut themselves down eventually, and then it should be safe to exit. Notice that this breaks out of the while loop here, so the whole application ends at that point. So now that we have the basics of the server implemented, just to handle connections coming in, not that it's going to do anything with them, we can go ahead and try to do the same thing for the client. So let's go down to our run function here, and then we'll create a def run listener. We'll put pass in there for now. We need to grab our threading library and our sockets, and we'll need struct later too. So import struct, import threading, import socket. So we'll need to do threading dot thread target equals self.run listener and start up that one. Now in here we also do another with socket.socket socket.finit, and then sock stream for TCP as S. This is the exact same as what we had to do to create the socket for the server. So s.set sock option socket.sol socket and socket.so reuse address true. So we want those. That's just the same option that we have, so that we can reuse that address. And then finally, we can connect to our server. So on the other one, instead of connect, it's bind. That's when you're hosting, and then use connect for anyone that's connecting. So one's definitively the host, and the other one's definitively connecting with TCP. So for this information, we can go ahead and pass in a host and port. We'll do what we did with the server thing, and we'll do a host equals 127.001, port equals, let me grab that random number. And we'll say self.host equals host, self.port equals port. Now we can put in self.host, self.port. So it's the same arguments as we use for bind. Like I said, the host will be different if it's a remote server. So you would still probably use something like this on a remote server, but then you would need the external address for any clients that are looking to connect, which I'll give an example of later. So let's go ahead and do s.set sock opt one more time. And for this one, because we're going to be sending, I want to do, where is it? Oh, it doesn't have it in here. iproto TCP socket.tcp no delay. When you're making games, this looks like something you would want to set to true. You want to turn on this no delay flag because you want all of your packets to be processed on the network as fast as possible. Just like send out without getting clustered together. Because what happens is there's something called Nagel's algorithm, where under the hood TCP will by default try to bunch together your packets, the things you're sending between the server and the client, so that it doesn't have to send as many different things across the network. And what ends up happening is that some packets will get delayed because of that. So you usually just want to disable this so that your messages get sent as soon as possible. And then we want to set our timeout to 1 and print connected S. Self.socket equals S. So I want a socket object that can be used by anything in here. So I'll go ahead and say self.socket equals none at this point, and then we'll just do safety checks to make sure it was actually set properly here. Just check to make sure it's not none. Then you know you have a connection. So in here, we'll be able to do our loop, but at this point, we should be able to connect to the server. I can only run one thing at a time in Visual Studio Code. So I'm in this code folder here. I can go ahead and do py server.py, and then over here, I can go ahead and create the client. And if you look, it's a bit small, but you can see new connection, and you can see the socket and an address and the port and all that information. So interestingly for you guys, this is not my actual external machine's address, so you can't DDoS me with this or anything, but that's because I'm testing locally. Anyways, so we can see that we have a connection here, and we have a connection down here too. So both sides are connected, which is good. I'll go ahead and kill this. And the next step is to handle the communication between the client and the server so that we can actually play tic-tac-toe. So the basic idea that I have for tic-tac-toe here is, well, very specific to tic-tac-toe. But what we'll be doing is that the server will regularly send out the game state to all of the clients. So it'll send the board information, whose turn it is, and if there's a winner or not. Then the clients will just send their moves, which the server will validate based on making sure the right person did things on the right turn, and to make sure you're not like trying to place something where someone already placed something, and to make sure you don't place anything once the game is over. In this case, our server will be what we call authoritative, which means that the server is making all the decisions as to what's allowed. So there's a trade-off in network programming where you sometimes do a lot of processing on the clients, and sometimes you want a lot of processing on the server. And the more that you do on the server, the less open to cheating your networking is. So for example, let's say after you made your move, the clients sent the board state to the server, and the server just took that and sent it to the other player. Now that case would be client authoritative because the server is not checking to make sure that that's a valid move. It's also sending a lot of data over to send the whole board whenever the players make the move. But yeah, because the server's not checking it, you're opening up people to cheating because they could in one turn place 3 pieces or something and then immediately win. So to prevent cheating, sometimes you want to have more checks on the server, which is what we have in this case. Now the downside of that is that it can be very computationally expensive to run all of the checks for all of the players on the server for some games. So there is very much a trade-off there in how much you want on the server. In a lot of cases, it's actually easier to code the checks on the client. I'll give an example of when you might want the client to be authoritative though. So let's say you're in a 3D world with physics and you have players running around. You don't want the server necessarily, depending on how competitive your game is, to be running all the physics calculations for every single player for every single frame that the players are behaving in. There are some tricks you can do, like validating the movements afterwards, but usually you'll have some level of client independence there. And another thing you got to watch out for is that if the server were completely authoritative, where you're just sending kind of your inputs to the server, the movement would be delayed, which let's say you're in a first-person shooter, you don't want to send, oh, I'm turning to the right a little bit, to the server and have the server confirm it, or else you're going to have all of your inputs delayed and the game's going to look horrible and make people sick. So there's some mixing you can do there. You can do your own research on whatever genre of game you're trying to make to see what techniques are out there for dealing with these types of issues. There's all sorts of tricks to deal with the issues of cheating and the delay from the network that you can look through. Back to what we're doing though. We've got an authoritative server. It's actually super simple in the case of Tic-Tac-Toe, so we'll continue with that. Now, aside from how we just structure our network architecture in terms of who has the authority on different things, there's also the question of how do we communicate the different ideas, the messages that we're trying to get across. So like the game state, for example, and players making moves. There's a couple different approaches that are built upon the idea that you basically have a send and receive feature. That's all you have, is you just send binary data or you receive binary data. A common model people think of is the request response model. This is actually what's used in everything on the web, where a client sends a request and then the server sends something in response. So for example, the client could request the game state and the server could send the information about the game state. Or the client could say, I want to make this move, and then the server could respond saying, okay, the move is valid or the move wasn't valid. Or you could even simplify that further and say, I want to send this move, and then the server responds with the new board state. That is a perfectly valid way to handle tic-tac-toe, and actually that's a pretty good way to handle a lot of non-real-time games, although it is at a base level a bit more work to set up. So I'll be using a different approach, which is kind of more in line with the model that I use in a lot of my games that are more real-time. So there's the idea of just kind of like unrequested data streams where the client just sends information to the server as it needs and the server sends information back as it needs, and it's not necessarily a request and response situation. There's a lot of performance benefits that can come from that and just kind of blasting all the information across as it becomes available, but it can also be a bit more of a headache to work with. In our case, it actually simplifies things a bit, which is why we're using it. Another model that people use is the idea of RPCs, remote procedure calls. So this is something that's actually not hard to set up if you want to take the time to do so after following this tutorial. There's this idea you put a decorator on like a function to mark that function as being a procedure that other programs on the network can call. And then when you call that function, all you have to do is send the function kind of ID and the arguments that you want to pass into that function over the network so that different programs can call functions on other machines across the network. And it's just another kind of abstraction people use to make multiplayer games. This is actually, I think, what you'll see by default in things like Godot. All right, so now in the server, let's jump over here. What we're going to do is we're going to create our listener. So we want to create another function, self-con, and this will be called in another thread because we want it running asynchronously. So we'll add to our thread count and then subtract when we're done. We'll want to copy out this thing so that we don't have our packets getting bunched up on this connection. And then we also want to set our timeout to 1 second. And finally, with con, While not self.kill, we want to run our loop to receive our data. We'll do try, and then except we've got our socket.timeout, which we can just ignore. And then, so the way this works is that we just receive data, and it's just a binary string. So if you've ever seen just bytes in Python, or ABC, so the B prefix means it's binary. But yeah, you just receive binary data, and it's in the bytes type, and you have to work with that because that's how it goes across the network, is in the forms of bytes, because that's the lowest level of data. Anyways, so we'll do data equals connection.receive. And there's one argument for this function, and this is the amount of data we want to receive. Normally I just put this at 4096, that's 4 kilobytes. You could set it lower. It doesn't really make too much of a difference where you set it at, as long as it's large enough for your needs. I believe there are some upper limits though, so I like to use 4096. Anyway, so we'll do if length of data. So if we have data, because sometimes this can be empty, and in that case you just kind of ignore it. But if we have any data in there, we need to work with it. So normally you would make sure that you actually have enough data for whatever you're expecting to receive. But in this case, we only need 1 byte. The clients can only do one thing, and that's place their pieces. And the information needed to place a piece can be represented in 1 byte, which is what we're going to do. And that's the smallest unit that you can receive. So there is no amount of data that you could receive between 0 and the amount of data to make a move. So all we have to actually do here is say target space equals struct.unpack from, and then b data 0, 0. So struct.unpack from will take a data buffer of like binary data. That's the data we're passing here. And then it also takes a format of what that data's format is. In this case, we just pass in B. I recommend looking up, and I'll link this in the description, the different identifiers you can use. Like for example, D is for a double float, or there's S for strings, but that's a single character of a string like that. So you do like 6S if you want like a larger string. There's also like I, that's like an integer that's unsigned. But yeah, so what we have here for B is 1 byte of data that's unsigned. If we wanted it to be negative 128 to 128, I think it's just B like that, but capital B is unsigned, so we do, that's 0 to 255. And then this last part is just the offset. So unpack from can take a buffer that's larger than what we're unpacking from, and you give it an offset, and it can read from there. And we always want to read from the beginning. There is unpack like that doesn't take an offset, but that requires that the amount of data you have matches this, which would have to be 1 byte, but we could feasibly receive more than 1 byte of data here. And in that case, we just kind of throw it out. It really shouldn't be happening because players make a move and then wait for the other player to make a move. So realistically, the server should get to processing it before any more data comes through. So we could just kind of throw out the extra data, which is what we're doing here. Now, the next step is to actually make the move. But to do that, the server needs to understand what's going on with the game. So thankfully, with Tic-Tac-Toe, I already have a lot of the game logic done for us. So I've implemented the board as a single list. You might think, oh, it would be easier to have the board as a 2-dimensional list where your dimensions are your X and Y of the board, but it's easier to convert into binary data as a single list, which is why it's like this. Anyways, and also if you're not familiar with this notation, this just means that you get a list of 9 ends here. When you multiply a list in Python, it just concatenates it with itself that many times, so you just end up with 9 ends. So we need the information to have the board state, so we're going to go ahead and copy this information. And we also want the winner, the teams. These 2 rows are just for, or lines are just for rendering stuff. So we just need this information, I think. So with that, we also need to be able to do a couple of things. This is the basic functions of Tic-Tac-Toe. I can just copy paste them in here. Place will place something into the board based on an index. And then this is a 2-dimensional lookup of the board. We'll use this in the algorithm to verify if a player's won. So this is where the server is running the validation to make sure that a player won rather than one of the players doing that work. And that way you can't cheat. So we have all this information here. We have the board, we can place things, and we can check if someone won. And this placing algorithm already verifies, hey, there's nothing here, right? And also make sure that it's at a valid location within the board. There's only 9 spots on the board, so you just gotta make sure it's valid. And then once those 2 checks pass, we can go ahead and assign the piece, and the piece will be either X or O based on the turn. Now, if you think about it for a moment, there is a little bit of extra stuff we have to do because this is the server now. Before, we had one game where both the players took turns and you could place and keep placing. But something we have to check is to make sure that you're not trying to place when it's not your turn. So we have this logic here that places a piece based on whose turn it is, but the loophole here is that if they send another request to place something, then it would place the other player's piece, which we don't want. So what we have to do here is in our place logic, we need to also accept the connection that's trying to place the piece. And what we'll do here is we'll do player ID equals self.players.index connection. If you remember, we were appending the connections to the players list, and we can get an index of the player by looking up that connection in that list. So this becomes either 0 or 1, which we can use to figure out which team this player is supposed to be on. And then the last thing we do here is to check player ID is self.turn. Oops, I didn't mean to put that underscore. There we go. Turn mod 2. So just make sure that the player's ID matches the turn that we're on, so that you can't place something if it's not your turn. You can also simplify this part and just put in player ID for the team, just because it's 0 or 1 in that case. You're also not getting the player ID from the clients, which is nice because otherwise the clients, if they could say who they were, could just lie and say they're the other player and make a move. But in this case, because it's all server side on who's who, the server keeps track of which connection is which. You can't cheat that part. One last thing I'm going to do is make sure that the self.winner is self.null character. We don't want the winner to be determined and then someone tries to make a move after the game's over. So over here, I'm going to set winner to null care or care, whichever. And the purpose of that is that when we go ahead and convert this into binary data, we don't want to deal with multiple data types, because before it was none or a string. Now I just have it as a string, which is why we're doing this. There's actually a real null character, and the binary representation of this is 0. So that's the null character. You can escape into it to get it, but I'm just doing n here for simplicity. So now that we have the ability to place, we can go ahead and take our target space here and do a self.place with this connection into target space. And with all those checks, if it's an invalid request, it just kind of gets thrown out, so we can just ignore it at that point. So now we have the ability for clients to send data, or at least the server to receive data sent by clients and update the board. Now we need to make it so that it can determine a winner and update that information and send the board information to all the players. So getting the winner is simple. I actually have this in the base game down here. Use check win. That's the function I made. So self.winner equals self.checkWin. And we also have to go in here and add a default return. And instead of returning none, we return null character if there's no winner. And if there is a winner, it just returns which piece won, either X or O. So we just get our winner if there is one. And then we do for player in self.players. And then we'll try to do, remember these are the player connections. So actually for clarity, I'll do player connection. We'll do player connection.send, and then we'll put something in there later. For now, we'll just leave it as blank data. Except, or we need a try and accept OS error, which can be thrown if your socket is messed up. In which case we just pass, and we're not going too far into error checking here because there's all sorts of errors you can get from sockets. Most of them just mean that your connection was broken in one way or another, and you just kind of have to shut things down at that point. But handling all that shutdown stuff elegantly can be like half of the work, but it takes a lot of boilerplate that isn't exactly fundamental, so I'll be kind of passing over that. So we can send data to all of our clients, and what we want to do here is send the game state. If you notice I have this sleep here, this means that we'll be doing a loop once every 50 milliseconds or 20 times a second, and we'll just be sending the information about the game state that often. This isn't the most efficient way to do this, but it works decently well, so that's what we'll be doing. So now the next question is, how do we represent the game state? So to do that, there's this idea called serialization. It just kind of refers to when we put all of our data together in just kind of like one data stream so we can communicate it in some way. In this case, we're going to be converting it into binary, and we have our whole board to convert. We want to include our board. We want to include if there was a winner, and we want to include what turn we're on. So we can just write a simple function here. We'll do def serialize. It'll be a one-liner. So we'll do return struct.pack. So this is the opposite of unpack. So if you saw over here, we have unpack from. I mentioned there's unpack, there's pack, and there's also pack into. Pack into can overwrite inside of an existing buffer, but we just want to make some new data to throw at the other clients. So we can just use pack here. So the format we'll use is BB9S, which means, and I recommend reading the documentation for struct. It's just like a one-page thing for the different identifiers. But that means we've got 2 unsigned integers that are each 1 byte, and then a 9-byte string. So the way we'll encode this is we'll put in our self.turn. That's going to be an integer, and the way tic-tac-toe works, there's only 9 spaces, so the turns can only go up to 9. And then that means that we're nowhere near hitting the limit of 256 that comes with 1 byte. If you wanted more space, there's H for 2-byte integers, or I for 4 bytes. There's another one for even more. I forgot what it was, but B is good for now, so we'll use that. The second part is the winner. This is actually a character. If you remember, it's going to be N, X, or O. So what we can do here is use the built-in ORD functions. It's just like one of the built-in functions of Python, like len. It just converts a character into its associated integer value under ASCII, under the ASCII format. So we'll be converting our winner character, which will give us kind of a value. I can demonstrate. You've got ORD A, and then it'll give you like 97, but like X would be 120. You can actually do math on that stuff if you wanted, but we're just encoding into a value that's within 1 byte. And then the last one we want to encode, and keep in mind when we're encoding all these, each one of these letters represents 1 argument. So it's turn, winner, that's the first 2, and then the S is the third one. The 9 just means that there's 9 of that in that sequence that apply to that 1 argument. I don't know if you can use it on things like B, but it exists for S where you're dealing with like strings. This is not an actual like Python string, so you can't just put like hello in here. The way it works is that you need to send a binary string. So what you end up with is needing to encode it into binary. So this would be valid to send, although it's not 9 bytes, so you'd have to do that. That would be valid. If it were like that, it's not enough data, it will give you an error, but it needs to be bytes data. So to encode our board, we're going to do a little bit of hackery. We're going to do .join on self.board, which will take a list of strings and merge them together if you aren't familiar with that. If you put like a comma in here, it would put a comma between each of the values, but we don't want that. We just want character after character, the 9 characters of our board. And then we would just want to encode it into binary. We'll choose the UTF-8 encoding. So there's different ways you could represent a string in binary, and we're just using UTF-8. And then this will come out to 9 bytes. So that's all it is to serialize our data. So we've got a way to turn in our game state into this binary data here. We can return it. So now we can just grab this, scroll down to our send thing here, and just do a self.serialize. And that'll generate all of the data for our board and send it to the client. So our server is pretty much done here. It can tell who the winner is, take moves, update the board, send out the information. So the last step now is to update the client. We can look at our listener function here. We've got our connection that was set up, but we're not doing anything with it yet. So let's go ahead and do something with it. So while not self.kill, and let's go ahead and implement the kill flag here because we didn't do it here. I'm going to be a bit lazier with this one. It's a bit more annoying if the servers don't shut down properly. And it's also got more threads. This one will only have the main thread and then the one we start for receiving stuff. The server can have a bunch of them running, so you have to be more careful with the server. So in this case though, when we quit, we just set self.kill equals to true. And we can just forget about it. We're not going to wait for things to shut down properly and count our threads because it's only one. So this one will be just running here, doing its thing. Data equals self.socket.receive. And we'll do the same amount, 4096 bytes. We need to accept our socket.timeout. And we'll do time.sleep 0.001. Oh, I need time. So another thing I need to talk about is the reason why I'm putting in these sleeps here. So there's some inconsistent behavior on different operating systems, and even if you put a timeout of 1, sometimes you'll just get an empty bytes array from your receive call here, and it'll do that as fast as possible. So when you have something where Python's making a call, it's ending up being a non-blocking function, and it's just constantly calling it over and over again because we're in a while loop, that will actually max out your CPU and make everything else run slow so you can't do anything. So you have to put a little bit of a sleep in here in those cases. You can be a little bit more elegant with how you approach this so that you don't sleep unless you need to. But putting in a sleep here just lets you be safe so that you don't accidentally max out your CPU and stop your other tasks from running properly. So I tend to put these on my receive threads so that they don't lock up. Anyways, we have our data, so we can just do if len data. We can do self.deserialize data. So now this one's going to be a bit more work. We can write our def deserialize self, and we can just take some data. And we'll say our update format equals bb9s. That is the format we specified over here when we're serializing. Like I mentioned before, you have to think about, do you actually have enough data? Because your packets can be split apart or they can be merged together, so you could get all sorts of messed up stuff in here. So you want to make sure that you actually have everything you need. So let's make sure that we have enough data here. So we'll do len data is more than or equal to struct.calcsize update format. So struct.calcsize will calculate how many bytes of data you should have for this format. So we want to make sure that we have at least as much as we need to decode it. Normally what you would do if you don't have enough is you just throw it into a buffer and wait for more data to come in, and then you process it with the combined data. But we're not doing that here because in most cases we'll get what we need, and I don't want to go through all that boilerplate. There's also the case where you get more data than you need, and we're not worried about throwing stuff out because the server's just going to send this information again. So if it happens to get 2 packets in because your connection stuttered and you've got your 2 packets in your queue to receive, your second one's going to be thrown out, but that's not a huge deal. You'll be up to date once you get the next one after that. So for this, it's pretty straightforward. We'll just do turn winner board equals struct.unpack from, which I talked about before, bb9s data 0. So offset of 0, there's our format. Actually, we can just copy this here and put that there. Here's our format. And then we have this data, which is, this is going to be a number. This is going to be a number. This is going to be bytes, like 8 bytes. So we have to actually interpret all this information now. So self.turn is actually just going to be turn. That's pretty straightforward. Self.winner is going to be, that's not how you spell winner, equals character. This is the opposite of ORed. So it undoes, like it converts a number back into a character. So we can do character of the winner, and that will set that correctly. If character of the winner does not equal self.noChar, else none, because we're using none to represent no winner here. That's just a quirk of how I wrote the Tic-Tac-Toe client, I guess. And then the final part, which is the most interesting, is the board. So there's a little trick here. We just do list on board.decode UTF-8. So that will turn it into a string of 9 characters from our board, and we just convert that into a list, and that will match what we have up here. And the client will never know that anything changed, except that it has new data in there. That's all we need to deserialize. So the next step is to be able to make moves. In order to make moves, you just have to send that 1 byte that the server's listening for right here. Fortunately for us, I have a place function, and we can hijack this to put in what we need for placing things. So just delete all this logic. We don't want to update the board ourselves. We want to let the server do it. So we'll do if self.socket. If you remember that's none until the connection is established. Self.socket.send all This is how you send information. I use send all with the clients. There's a minor difference in that it forces everything to be sent. And then we'll do struct dot pack, our 1 byte, and then we'll just throw in our space index. So that's where we're wanting to make a move. And remember, this is just because I implemented this all as a one-dimensional array. This is one value. A lot of the reason why I did it, it's both easier to represent the board and easier to represent the moves when you've got an array and your two-dimensional move is converted into one dimension, which there are algorithms for converting it. This is it to convert a two-dimensional position into an index. So now that we have our place logic hooked in, I think we should have everything we need to run this. So I'll go ahead and start up the server and we can see if it's working. If I can click, I cannot click. Uh-oh. So something went wrong here. I found the mistake. Over here, we forgot to spawn the task to listen to the requests of the client. So over here in the listen loop for when we're listening for incoming connections, after we get our new connection, we need to actually spin up the thread that listens to that specific client. So we need to create a thread, and our target will be self.run listener. And our args will be, I believe, just the connection. Yep. And if you notice, I have to put a trailing comma in here because it's expected to be a tuple. But if you want a tuple of one item, you have to put a comma there, or else those get interpreted as parentheses for order of operation instead. So you need that comma in there just so that Python knows that it's a tuple. Anyways, let's go ahead and start the server again, and let's see if I can make a move. I could not make a move. And here's the other mistake. I forgot to put start there. You gotta actually start your thread. You can't just create it. So you can actually, there's other functions you can do with for threads as well. You could actually say your thread equals that, and then you can go and start it, because the thread is an object. But I'm just starting it in place, and then we just can forget about it. But yeah, so we have to start the thread. That's also important. So now we can make our first move. If you notice, we can't make the second move. So this is where we have to go ahead and get a second client. So I've got this here. I'm going to do pi tic-tac-toe. And it opened up. Because the server is constantly broadcasting the game state, the other client knows immediately. Once the server sends the information, it gets everything about the game state. So it can connect late. It's not a huge issue. So the second player, the second one to connect that is, can place the O. So I can't place anything here right now. But on this client, the server knows this is the other player. I can go ahead and place an O, and then we can go over here, and let's go ahead and try and block this. And you notice I can't place anything else here, and we can go there. And at this point, the circles have lost, so we can just do that, and it says X wins because the winner field updated, and that's also included. Yeah, so that's pretty much working tic-tac-toe. So for the next step, I want to put it on my server, and then we'll run it there. So this could look differently in different cases. In my case, it's just like kind of a Linux machine. It's a VPS where I can do whatever I want in it. It's already got my port set up for me, and I literally just put it on there and run it, and then point the games at that. And we can be testing this, like literally you watching this, if I wanted to, could play tic-tac-toe with me over the internet. Personally, and this isn't like an actual sponsorship, I've been using Linode. This is just kind of an option for you if you want to have a remote server. You can use something like Linode for virtual private servers so that you can run like multiplayer games and have like a server that isn't your home computer. There's two issues with using your home computer for game servers. First one is that you have to expose your IP address unless you run it through a proxy, which usually also costs money. So you might as well just have an actual server. But yeah, you can get DDoSed, and that can disable your internet so you can't use it for anything. People can also use your IP address to figure out roughly where you live. The last issue is that in a lot of cases, you can't even do it in the first place. So there's this idea called double NAT where you end up behind multiple layers of routers. And normally, like the default for most routers is that pretty much all the ports are closed, which means that you can't accept inbound connections. This is just kind of a security thing. And you have to go manually open them and say, this port needs to go to this machine and do this or whatever. Now, what happens is you'll have your router for your house normally or whatever. But in a lot of places, like if you're in like certain neighborhoods or if you're in an apartment complex, they'll have all of those kind of linked together into another router. So you're behind two routers, and that second router you don't have any control over because it's also for all your neighbors. And because of that, you can't say, I want something making a request to that address on the open internet to go to my machine because you don't have control over that. So in those circumstances, you can't set up anything that can receive connections from the internet. You can make connections, you can go make outbound connections, but you can't have anything going inbound to start connections. That's one of the main reasons I initially got into using VPSs. So Linode's what I've been using. I've just been using it for like, I don't know, like I think 5, probably like 7 years now or something. Support and uptime's been pretty good. I recommend doing your own research because there are cheaper options out there. I know another one that was popular at the time when I was looking around was DigitalOcean. There's a lot of different options nowadays, so do your own research. But if you are interested in using Linode, you can save me a little bit of money if you use the referral code in the description, which is like they didn't pay me for the sponsorship, but it's just a normal referral code which will give me credit, so I don't have to pay for my servers if you start using them. So that's just an option. Like I said, don't take this as you should necessarily be using Linode. It's just an option, so you can have somewhere to start from. It's basically just a Linux machine connected to the internet. It has its own address and everything, and you can run servers on it. And that's what I'll be uploading my server script to. So the server script will just leave as is. And then on the client, though, we'll want to specify our host. So if up here we have our keyword argument for host, and we're going to want to set that so that we're actually pointing it at my server. I actually have a domain name registered for it, so I can literally just point it at thefluffypotato.com, which is where I'll be putting it, and start it up, and that will point to my server, so we can run our demo with multiple machines connected to the internet. One more thing before we start that, though, is that if you want to kind of try this without buying anything, there are a couple options. There's the idea of using VPNs, some of which are free to use, although they can be sketchy, to get yourself on a virtual shared network where you can instantiate connections, and that gets around some of the port forwarding issues. The one from that people used for like Minecraft like a long time ago was Hamachi. And so this is like a different use of a VPN than what people think of when they think of VPNs nowadays. They think of like privacy and stuff, but there's other uses for them, and this is one of them. So you can do stuff like that. There are some free ways to do that. I think Hamachi still exists. You could try that. Another thing to consider, and this is what actually a lot of Steam games do nowadays, if it's like co-op, is they'll have the server be run by one of the clients, but they'll set it up so that it goes through a proxy layer that gets around the port forwarding, almost like you're in a VPN. And that proxy layer is run by Valve, so they're the ones paying for it, which can make it so that you can have millions of players and you're not paying for that communication, since the forwarding of the data is going through Valve. So that's a little bit of a trick you can use to get around the port forwarding issues. So that's what you might want to do if you're doing like a co-op thing and you're not super concerned about it being the most real time. It's not the most efficient in terms of communication because the client who happens to be the host that's running all the computations that the host needs to run, if they're out in, I don't know, Australia and everyone else is in America or something, everyone's going to be having a bad time. Whereas generally, if you set up a server somewhere in like a specific region, you can guarantee that if someone's like from that region, they have a good connection, everything is good. Whereas it's kind of like the lowest common denominator thing with those connections. So if the person who happens to be the host has a bad connection, it's just a bad time for everyone. So that's kind of the downside there. So there's always a trade-off with these things. It's just worth looking into. So let's go ahead and do our demo with networking stuff across multiple computers. Alright, so I've got Tic-Tac-Toe running on my laptop and my desktop separately. As you can see, there's no cables for my laptop here, but yeah, so I've got Tic-Tac-Toe on the desktop here. This is the O player and this is the X player. And I've got it running on my server. So if I go over here, I can go ahead and place the X and it updates both of them. I'm gonna sit back here so I can place the O and We'll put an X there, and an O here, and an X there, and an O there, and O wins. So it does work, and yeah, you can make pretty much any multiplayer game like this. It just takes a fair bit of work. And now, before you go, there's a couple more things I'd like to go over. First of all, there's ShobNet, which you may have seen me mention in some of my other videos. That's how I actually make multiplayer games with Python, and that's a layer built on top of Python sockets. So I'm using all the same stuff I showed you in this video. I just built a bunch of stuff on top of that to make it easier to work with. The idea is that it's built into Python objects, so you can modify an attribute of an object and it's automatically networked. So there's a lot of stuff for you. That's not done yet. I might make a separate tutorial for that if I finish and release that. It's also not foolproof exactly. Should become more tested over time, but I wouldn't consider it to be super stable. So it's good to understand how to do this stuff yourself. Hopefully ShobNet will be public in a year or two, but we'll see. So in terms of this implementation for networking for Tic-Tac-Toe, there's a couple things I'd like to kind of add to it, the way that I've implemented it here. First of all, we're not really considering disconnects and reconnects very well. The error handling is a bit messy. I did a little bit of it, but you might have to deal with it as you go. There's a lot of different errors that can be thrown. You need to be handling them all properly. You can just kind of find those as you like playtesting and stuff like that and add the cases for them as you go. One big one that you might want to catch, for example, is the connection resets or aborts. You can just do that or that and break that. It's common for connections to shut down and then you get that error, so you might want to accept something like that. The OS error one can also happen as well, so there's a few different, I think like 4 or so different errors that you might have to catch and handle differently depending on what's happening. There's also ways to shut down sockets and like basically communicate that a connection was properly closed. There's a shutdown function, and there's also the close for the actual like more client side or the local facing closing as well. Some stuff to think about implementing if you want to mess around with this. You could implement restarting. So like when someone wins, you might want to restart the game, like clear the board and start the turns over. But you want to have time for players to actually see the results and stuff, which is why I didn't mess around with adding that, because it's kind of irrelevant for understanding the basics of networking. But that's something you would normally add. As an exercise, you could try scaling up this game to 10 by 10 spaces, for example. Maybe you have to get 5 in a row or something like that. But keep in mind, though, your data restrictions, for example. So in a lot of places, we used 1 byte to represent a space. You might need more than that if you've got a grid that's larger than the maximum amount of spaces. If you got 100 spaces by 100 spaces to create a 10,000 space board, then that's not going to fit in 1 byte. So you're going to have a larger field for that data. One final thing I should go over is the idea of message splitting. Normally, you would want to split up your messages and process them independently and have a strict idea of what a message is and where one starts and ends, so that you can process things in a stable way. If you notice, I threw out data in a lot of cases, like right here, I took just the first byte and threw out everything else, because either the other data is likely to be irrelevant, or because later data will correct for any errors from earlier data being lost. Normally, this is not the case. This is an edge case with Tic-Tac-Toe, so you'll usually want to implement like a way to break down your messages. This is a message format where you expect to see certain things and you know where a message starts and ends. Normally you do this with headers, where the beginning of a message is like, for example, your message type is one field. You might say how long your message is so that you know where that message ends. And then when you get your data coming in, you just keep adding to it until you have enough data for the message you've received, because you'll know from the size that you have in your header. You always know that you want to see a certain amount in your header, and then after that you want to make sure that you have enough for the message you're expecting based on your header. That's generally how headers work. So you like build up a buffer until you have enough for your message, and then you go and process it. So that's normally how you do that, and then you can build other stuff on top of that that's more convenient, like remote procedure calls, or you can do request response type stuff, or you can do like the shared objects I have in my framework. There's a lot of different approaches you can use that are built up on top of messaging, but in most cases you want to be able to break apart your messages. When it comes to testing to make sure that your code is stable in terms of netcode, there's something called Clumsy that you can use. So this is Clumsy. It's a little bit small. What it lets you do is it lets you mess with all sorts of things with your network connection, and it actually tests your local connection as well. And you can like induce lag, drop packets, you can throttle stuff, duplicate, make it come in out of order. You can modify certain ones and do all sorts of weird things that can happen on normal network connections to make sure that when things go wrong, that your code handles it correctly. Now, most of these, though, are covered naturally in TCP. So, like, for example, if you drop a packet, TCP will find out that that packet was dropped and then go and resend it. But what happens, though, is that because it also guarantees that it's that it's in order, so this one also gets corrected, what ends up happening is that everything gets held up, and when you call .receive on whoever's receiving, you're not going to see that data until the data gets there and that you have all the data in order for what you should expect to see. That can cause some delays that UDP wouldn't have if you didn't have those requirements enforced, but it also kind of deals with these things for you. But these can force some stutters on you, and the main thing to test is just lags and stuff like that, lags and drops, just to cause it to stutter with TCP. And then you can get a feel for how that looks. You can realistically put in like a certain amount of drop, because some people just have bad network connections, especially over Wi-Fi, where they're dropping a certain amount. And maybe your code should handle those stutters of data coming in from the drops in a different way. So one way this might matter is, let's say you're representing a player moving in a world, and the packets get dropped, and then suddenly you get new data, and it looks like they teleported. They're like way over somewhere else because some time passed with no valid data being processed. So what you do in those cases is like you'll use like something like interpolation, dead reckoning, and stuff like that. So interpolation is when you take multiple samples of data and then you interpolate between them, like you create values in between like position 1 and position 2 to figure out where you could represent the player being based on time. Dead reckoning is where if you run out of data for representing, well, for interpolation normally, you approximate where something should be next. So it's a good example would be a racing game. I don't do this in PixCarts, but in a racing game you might want it to be that you know where a car is roughly going and they can't turn super sharply. So you can just kind of assume that they're either like they're turning or going straight. You can kind of keep that current angle of motion and keep having them go forward even though you don't have any network data. And then when the new data comes in, you can go and interpolate it to the new position, so it can just slide over to where it actually is. So to do that, you also have like a buffer of the data under the hood, and you're only using like certain amounts of it, and then you end up a little bit behind. So there's trade-offs there where what you're showing on screen is a little bit behind just so things can look smooth. So those are just some of the techniques you might put into networking. There's all sorts of stuff for like different genres of games. You can look up how people do the netcode for different types of stuff, because ultimately there's a physical limitation on netcode in that if you're in America and you're sending something to Australia, you're going pretty much to the other side of the world. Actually, I think India is closer to the opposite of America, but although they're both still in the northern hemisphere, so not quite. It's like, what is it, South Indian Ocean? Anyways, if you're going to the other side of the world, there's a physical limitation called the speed of light. And if you do the math on it, if you take the diameter of the Earth and you check it against the speed of light, you'll find out that you can't actually even get the information to the other side of the Earth in less than 40 milliseconds, which means a round trip is going to be 80 milliseconds. And a single frame in a 60 FPS game is 16 milliseconds. So you've got several frames there worth of delays at a minimum. In a lot of cases, people have like connections where they're dealing with like 200 milliseconds of latency. So ultimately, there's all sorts of restrictions that come from the physical delays in networking, and you have to creatively work around those. And it's just kind of interesting how different games approach these problems, and I recommend doing your own research on the types of game you're trying to make, because it's different for all of them. Anyways, if you want to check out Clumsy, I mean, it's completely free. A lot of people use this. This is just a normal application people use for networking stuff. I'll put a link in the description so you can go use it for your own projects. Anyways, I'm starting to lose my voice. This is a long tutorial. Thanks for watching. I hope this was helpful. Hopefully I'll do a video on ShopNet in the future sometime when that's ready, which will be maybe like a third of the length because it does so much stuff for you. But thanks for watching. I'll see you guys later.